Hello friends, in this series we are learning string to string library from Stanford University. In the previous two videos we have looked at how to compute the distance and similarity between two strings or texts or documents. Okay, so in this video we will look at search. Now as we know there are two types of search. The first one is lexical search, which is more of traditional keyword search, right? So we have a document and we have a search string. Within this document, we will search for the keyword or the exact phrase, right? That's what the traditional lexical search has been. But recently, semantic search has becoming more popular because of the advancements in embeddings as well as vector databases. Okay. So within lexical search, we have three algorithms. Now all of them will be taking exactly the same form of input and giving the same output. How they arrive at the solution is different, but all three will be producing exactly the same output. And then we will look at the semantic search using the Facebook library called Faiss. Okay. All right. So the first algorithm for the lexicon search, it's known as this Robin Karp search algorithm. Now this algorithm, it takes a hash function to do the hashing of the strings in order to find if the search string exists in the document. Okay. Now any hashing function, they take in general much larger size data. For example, it could be a paragraph or a sentence, or it could be even an image of arbitrary size, and then map the input data into a fixed length, much smaller size output data. Okay, this is also sometimes referred to as fingerprint. For example, we might have a text of size, let's say 1000 words, and using the hash function, we can map it to, let's say, a string of 100 characters. Now, we might have another paragraph of, let's say, even 2000 characters. That one also get mapped to the same length of 100 characters when we do the hashing, right? Basically, that's what the hashing functions do at a high level. Now this algorithm, it takes a hashing function. So we need to provide one. Now we'll provide the default one. Don't worry about this base and module. Those are the default parameter. So when we initialize this algorithm, we simply need to supply a hashing function. In this case, we are using this polynomial rolling hash. Okay. So don't worry much about it. I mean, we can just use these as defaults. Okay. Now comes the interesting part. So here we have a text. So basically a bunch of books like Sense and Sensibility, Pride and Prejudice, etc., etc. And these are written by the author name Jane Austen, and are important works of English literature. Okay. So this is our text. And then we are searching for pattern, the author name Jane Austen. Okay. Now, again, these time functions, we are just using them to see how much time it would take for this algorithm to do the search, but not important again. Okay. So the syntax is exactly the same for all three algorithms. It's just this algorithm name, and then we would do the search with two variables. So one is the text, the actual text in which we want to do the search, and then what are we searching for? The pattern. Okay. Now it returns the index within this search, within this text, where the pattern is found, if it is found, right? Okay. So here we have a bunch of print statements. So all it is doing is, okay, it is saying, hey, I found the pattern at position number 127. So for example, if we count from here S1E2, and our author name J-Neston, it's at position 127. So the character J is at position 127. Okay, and then it took a tiny fraction of a second. Okay, 10 to the power minus 4 seconds. All right, now here we have a different pattern, and if the search pattern does not exist in the text, it will return the index as -1. So -1 means it is not found. Now the other two algorithms, so the second algorithm KMP, it works, the input output is exactly the same, but how it arrive at the solution is different, right? So again, we have the same pattern and text, initialize the algorithm here, and then to the algorithm supply the two variables, the patterns and text, and use the search function. It does exactly the same, again same output, and this time it took slightly less time. Okay, and the final algorithm, base Moore algorithm, it also does the same thing. Again, we are using the same text and pattern, does this exactly the same, and it found the same answer. Okay, so all three algorithms are doing exactly the same. Now comes much more interesting part, the semantic search. So as I mentioned, semantic search has been becoming more and more popular. One, because of the advancements in vector databases, embeddings, and large language models, etc. And the second reason is we have a few limitations with the keyword search, right? Sometimes the document may not have the exact keywords, but it might have the relevant information, right? So using semantic search, even if the document does not have the exact keywords, we will be able to find it out if it is actually relevant. So our intent and the context, etc., are taken into account using the semantic search as opposed to the lexicon or keyword search. Okay, so we will be using this FAISS library. So it's Facebook AI semantic search library. Okay, now this library, it's a highly efficient library for mainly for two things. One is for doing the clustering, and the second one is doing the similarity search on dense vectors. So these dense vectors are the embeddings. Okay, now so we import the function. Now when we supply large text, we will be doing two things. One, we will be tokenizing the text. So we will have a tokenizer model, and then we will be creating the embeddings. So there will be a model to create the dense vectors or embeddings, right? So those are the two models we are supplying. It's the same model in this case. Okay, all right, we initialize the model, and then here we have some corpus or the documents, right? So each sentence is a document. Now this need not be just one sentence. It can be a paragraph, it can be a book, or it can be anything, as long as the number of tokens does not exist, does not exceed the model requirements. For example, different models, they have different token limitations. Some might have few hundred, some have couple of thousands, etc. So in general, if the document is too long, we break the document into much smaller pieces and then do the embeddings. Okay, so here is our corpus, and then here we are indexing the data. So what I mean by that is, here we are providing the corpus. Okay, so it will be processing these documents one by one, and it will be creating the embeddings and storing them in this variable. Okay, so we have about 25 documents, and this function will take quite some time because it has to create the embeddings for those 25 documents. Now, as you can see here, it says it has 25 rows, and it has these two columns. One is the original text as it is, and then we have the embeddings. Now, if you want to see what are all the functions we can do on this, you can see here, right? So we can add the indexes, we can create embeddings, we can do the search, we can get what model has been used, what tokenizer has been used when initializing it, etc. Right? So let's just take some dummy string and create embeddings. Okay, so here we have taken a text, which is text in this case, and we have created the embeddings. Now this variable, it's a tensor, and if you look at the size, it's 1 by 1024, right? So this model, it creates embeddings of size 1024. Where is the model? Yeah, here we have the model. So Facebook bot large language model, it creates embeddings, or it map the text to a vector of dimension 1024. All right, so we have indexed the document. Now, because this is a small corpus, we are doing locally, right? We are everything in memory. But when we have large amount of documents, millions or even billions of documents, we generally use a vector database. Okay, but for this short corpus, we can do in memory, and then we do the search. So we have indexed the documents. Now we are doing the search. So in order to do the search, we'll just use the same set variable, and we perform search on it. So this is basically we can call it an index or vector database. Okay, so we need to supply two variables, right? One is the query. So in this case, we are looking for all documents which are semantically similar to I like going for a run in the morning. And then we are asking for top K documents, in this case 5 documents. So from this corpus of 25 documents, we are trying to find 5 documents which are semantically similar to this piece of text here. Okay. All right. So it written a nicely formatted data frame with 3 columns. One is text, and the second one embeddings, and finally the score. Now, unfortunately, the score is not normalized, but the lower the score, the better it is. So what it is saying is, for this given sentence, this is the sentence which is most semantically similar among the 25 sentences we have. Okay. So here we are saying, I like going for a run in the morning. And this one, I always try to make time for exercise. Okay. So as you can see, these two are referring to similar thing. And then the remaining 4, I love listening to music while I work. So here we have this work. Now, please note that among these 25 documents, we may have only one, or we may not have any document which is semantically similar to our query document. But still, since we have asked for 5 documents, it will return the top 5 similar ones, even though the similarity score is very, very low. Okay. All right. So these 3 sentences are also, even though they are not directly related to run or workout, they are sort of doing some activity, right? All right. So then it's just we are printing the same thing, more like a text. And let's do one more query. So here we are saying I'm interested in cooking and baking. Okay. So we are asking for top 3 similar documents. Now, the first one written, cooking is one of my favorite hobby, which is good. And the score is also low, 149 it says. I wish they would have normalized this score to between 0 to 1. Okay. And then this is not about cooking, but again, it's kind of hobby, right? So hobby wise, these two are similar. So I love traveling and experiencing new cultures. And finally, it says again, hobby. I love listening to music while I work. Okay. So among these 25 documents, only one is referring to cooking, but we also have 2 other documents, probably more, related to hobbies. So that's why when we query for this document, which is about cooking, among the 3 documents, the semantically most similar one is also about cooking, and the remaining 2 are about hobbies, because cooking also a form of hobby, right? That's all for today. A very quick summary. So we have two types of search: the lexical search, which is also keyword search. We have three functions in the library. They work exactly the similar way. They take the text and search a string as an input, two variables, and they will return the index if the query string find within the text. And then we have semantic search. For this, we have used this Facebook library. So basically the given documents, they converted into embeddings, and then our given query also gets converted into embeddings, and then it does the similarity search using some sort of metric, in general cosine similarity. Okay, and it will return the top n documents. All right, that's all for this video. Thank you very much.